All right. Good afternoon, everyone. Welcome to another IEEE GBM. I'm Alex, and today we're going to be talking about wireless communication. We're going to be, oops, wrong button. So yeah, we're talking about wireless communication, and we're going to go over, essentially, you have data in one place, you want to get it somewhere else. How do you put that data onto a signal? How do you make sure that you achieve the correct error rates? How do you actually transmit it? And, what are some wireless communication protocols being used right now? So the engineering challenge is that you have to transmit data from one device to another one, but you might not have a wired connection available. If you do, then a lot of the stuff we'll learn today is still applicable, but the transmission method would be just a wire. To start, we already know how to make a signal, meaning that if we have a voltage on a wire, we can measure it. We can measure the voltage, the current, and the frequency if it's a alternating signal. And we can also change those as well using various circuit components that you'll learn in your computer engineering classes. What we want to do to transmit data is we want to modify the wave so that the data is represented by it, and you'll see that in a second. Right now, what we know for voltage is that we can either have a DC wave, which means that it doesn't oscillate in time, or we can have an AC wave. And in most cases, AC waves are going to be what we want to use. Back when they were figuring out electricity and how to generate power and send it to everyone's houses, there were big arguments over whether to use DC or AC. And eventually they decided on AC, and that's what runs through your house, that's what runs through Ethernet cables and the power lines that you see outside. We use AC for almost everything because it loses less power over time and over distance that it travels, and it takes less equipment to maintain a AC wave. So we want to put the data onto an oscillating signal, an alternating current signal. And we can do that in three different ways. So mathematically, we represent a wave using some amplitude times a cosine of the frequency and a phase offset. You can see on the right here that when you change the amplitude, it'll increase the height of the wave. If you change the frequency, it changes how often the wave oscillates. And you'll learn in your physics classes that the period of a wave, can I draw? I think I can. Pen. The period of a wave is from one peak to the next peak. And the frequency is how often that wave occurs in a second. And then if you change the phase is the offset from when it starts. So here is a wave with 0 phase, and here is a wave with a phase of, I believe, pi. So this would be plus pi. And what this offset does is it allows us to change when the peak is. And so these are the three things we can change in a wave. And we're going to use those to apply data. So let's say we have data that we want to transmit, and we want to put it onto a wave. So we're going to change the amplitude of the wave to represent the data. Here is 1, 0, and if you split this, you can see there are 3 ones here. 1, 1, 1. So this represents the digital version of this data here. And what we do is we say when we want to transmit a 1, we set the amplitude to 2 volts. When we want to transmit a 0, we'll set the amplitude to 1 volt. And you see that here. We have 2 volts, 1 volt, 2 volts, 1 volt, 2 volts. And that has the same shape as this digital wave here. Now, we don't typically use 0 volts as a transmission. So we don't say, when we want to transmit a 1, we use a 1 volt, and a 0, we use 0 volts, because no wave at all isn't necessarily that we're receiving a 0. It could mean that we're not receiving a signal at all. And we don't want that, because there's no way to determine which one we're getting. Have we lost connection? Are we not receiving a signal? Or are we receiving a 0 bit? So instead, we'll use some non-zero amplitude. That way we know that we are always receiving the signal because we're getting something. And this is called amplitude modulation. Modulation is the term that we use to represent putting data onto a wave. We typically use a frequency that's much higher than our modulation rate, which is the rate at which the bits change. That way we can get multiple peaks and lots of measurements for each bit that we transmit. So we can pack more than one bit into a symbol. And a symbol is what we call one of these time frames. So in this case, the symbol is 1 bit, but we can pack 2 bits into a symbol by using different modulation techniques. So this is called quadrature phase shift keying. And the phase shift keying means that we are changing the phase of the wave. So if you remember our cosine function that had some frequency plus a phase, we're now changing the phase of the wave. And what we represent here is that these are all on a unit circle, which means that the amplitude, which in this case is the P, is constant. The benefit of keeping the amplitude constant in this case is that we don't change the power of the wave, because if you change the voltage in a signal, it changes the power you have to transmit. So we can keep a constant power that we're transmitting, but we can change the phase, and now we have 4 different phases that we'll transmit. So what that means is that at any time, the wave will have one of 4 phases. In this case, pi over 4, 3 pi over 4, and so on. What we do to pack that in is that one symbol now represents 2 bits. And we can do that because we are using 2 different dimensions. So we have the in-phase component and the quadrature component. Before, when we were doing amplitude modulation, it was 1 dimension, and that's the voltage that's here. But since we have 2 dimensions here, we can represent a 2-dimensional system. So we can transmit 2 bits in 1 symbol.
Quick question.
Yep.
Is that using gray code for the?
It is.
Okay.
Yep. And that's a really good point, actually. The reason we use gray code, which gray code just means that adjacent bits only differ by 1 bit position. So as you can see here, it's 0, 0 and 0, 1, and if you go the other way, it's 0, 0 and 1, 0. So only 1 bit position changes between each point. And we'll get into what that means, but the benefit is that if you have an error and the received signal is this one, but you sent the 0, 0, that means you only have 1 bit position that gets messed up. If you made this guy 1, 1, and you had that same error, you would get 2 bit position errors. which is the benefit of using gray code here. Now, for those of you who don't know, if you haven't taken 330 or I think 323, the in-phase and quadrature components of a wave essentially say that we can split this wave into two perpendicular waves, and we call those orthogonal waves, which means that we have some quadrature amplitude times a cosine. They usually have the same frequency plus a phase, and then we have another component, cosine, plus that, plus 2 pi, not 2 pi, pi over 2, a quarter of a wave. And that this addition of plus pi over 2 actually makes these two waves perpendicular. And the reason that we would break a wave into two perpendicular waves is because it allows us to work in a two-dimensional space, which just helps with a lot of mathematical operations. So that's in-phase and quadrature components. There are a lot of different constellations. We're going to keep looking at QPSK for right now, and we're actually going to talk about gray code a little bit more. So let's say we transmit the signal where our signal is S of t, that's that cosine that we've been looking at, and when we receive it, our R of t, the received signal, is the sent signal plus some noise. There's some noise in the channel we send. It could be a wire, it could be a wireless channel with a lot of interference, but there's some noise added. And what that means is that our original signal, S of t here, actually has some noise added to it, which gives us R of t, this signal, R of t. And so instead of receiving this point, this modulation, we actually receive this modulation, which means that we receive a different phase and a different amplitude. So what we're able to do is we're able to map out, essentially rotating this noise line around in a circle, we're able to map out a circle of probability. And I've changed the gradient here to represent that most of the time the noise is going to happen right around the modulation point. And as you go further away, it becomes less likely that you have that much noise added to your system. And so what we're able to see is that the probability of getting an error that's all the way over here when you sent a 0, 1 is really low. But it also means that if you sent a 0, 1 and it's all the way over here, you're probably going to think that's a 1, 1 in the received signal. However, since if we know how much noise our system has, we can properly determine the space between these two that we need such that this will very infrequently happen. I hope that makes sense to people. The idea that we add noise to our signal. If we send a 0, 1, we add noise. If we send a 1, 1, we add noise to it, and that puts us at any point in the circle. And you can see that with the sampled simulation on the right. What we have are a bunch of points that we've sent, and they're distributed around each one. And we've spaced these enough such that if we sent a 1, 1, and maybe this guy is a 1, 1, this is extremely unlikely because the noise doesn't add this much variation to the signal. And if it does, it's one-off and it's very rare. But since it's closer to our 0, 1 point, we'd probably decode that wrong. And that's what we call an error in our transmission. So when you learn about error detection and parity bits, this is why we have those in place, because when we transmit stuff, we're going to have noise in our system, and it's going to change the signal we actually receive. And we have to be able to detect that an error occurred. Are there any questions about any of this? If not, I will keep moving on. So there are a bunch of different ways to do modulation. This is 8 PSK. So before we were looking at QPSK. This is 8 PSK, which essentially says that you now have 8 points. And since you have 8, you have 2 to the third options, which means you can do 3 bits. Now, as you can see, this guy, these two are much closer together, which if we talk about the noise, right, we can only have, say, that's the halfway point. Any point that occurs to the left of here, we'll say is this 0, 1, 0. Any point that occurs to the right is 1, 1, 0. So if our noise is bigger than this halfway point, we are going to get an error. We're going to decode this incorrectly. So we have to make sure that we choose the modulation scheme that will minimize the amount of noise that we get. If we have a very noisy channel, we'll want to use QPSK, the 4 here, instead of 8 PSK, because QPSK, the points are farther apart, and we can accept more noise into our system. But if we have a less noisy channel, then we can use 8 PSK, and now we're getting an extra bit into each symbol that we transmit on the wave, which gives us a higher data rate. There's also CAM, or QAM. This is quadrature amplitude modulation. And so the idea here is that you are not only changing the phase of the wave, so if we just use these here, we have our QPSK, but we're also changing the amplitude of the wave, the size of this circle. And that gives us a lot more points, and we can actually transmit 4 bits at once instead. And then you also have APSK. And this is technically called 16 QAM because there's 16 points. You can see on the right here that we're changing both the amplitude and the phase. And APSK is just like the circles, but we are also now changing the amplitude as well. And each of these have different characteristics for how they handle noise, how they perform with the amount of power they require, because changing the power level of a signal is expensive, especially when you're working on something that runs on battery or runs on very limited power, right? If you change the amplitude of a signal, that's going to take more power. So maybe it's better to have APSK, where there are a bunch of constellation points, a bunch of data options on one amplitude level. So you have to change the amplitude less frequently, use a little less power than quadrature amplitude modulation, where you're changing the amplitude very frequently. So it just depends on what system you're working with and which system you need. And a lot of modern systems like 5G will start with a lower data rate like QPSK, and then once they've measured the noise in the system, will swap to higher modulation schemes to get higher data rates, but still keep the number of errors down. And we can pack even more in. So what we've been talking about is modulation. the concept of getting ones and zeros and turning it into a wave. And then in the same perspective, demodulation is getting a wave and turning it into ones and zeros. And the way we do that is we measure the amplitude and the phase and the frequency of the wave we receive. And then we use our map here to say that if we get a phase of 0 and we have an amplitude of whatever amplitude this is, then we are receiving a 111. We measure that. And that's how we use demodulation. You can also do encoding. And encoding is what we learn with Hamming codes and CRC codes. And these are how you add error detection and correction. So what that means is I'm adding parity bits. I am modifying the data so that it's less likely to get an error. And if I get an error, that I can fix it instead of having to just retransmit until the error goes away. But we're not going to get into encoding because that's a little advanced for this meeting. But yeah, so there's an extra step. So if you want to transmit 8 bits that you've created, you are first going to encode it, which adds error prevention and detection capabilities. So you're going to add your parity bits to the end. You're going to do some other fancy math. Then you're going to modulate it onto the wave using one of the modulation methods we talked about, which just means that given a 1 or a 0, or maybe a set of 1, 0, 1, this could be a phase of pi over 4 and an amplitude of 2. And so you would send that part of the wave would have these values. And then you transmit that. And when you transmit that, right, this is your S of t. This is where you get the noise on the noisy channel. And then this is your R of t, where R of t is S of t plus N of t, your noise. And then you have to do everything in reverse to get back to the data. And hopefully the error correction capabilities you added and the modulation techniques you used make it so that you can get the same data back. So this is how we modify the data that you want to send and put the data onto a wave to minimize the chance of an error. But how do we actually transmit the wave? How do we get it from one point to another? And we're going to do that using electromagnetic radiation, because we're talking about wireless communications today. So electromagnetic radiation is the concept that if you have a single point that has an electric charge to it, it is radiating that electric charge. If you've taken physics 2, some of these things will look familiar to you. Now, this is a theoretical representation of it, and this could be an electron, this could be a charged atom, could be anything. And theoretically, we call this isotropic, which means that it radiates out equally in all directions. We call this an isotropic wave. Now, this is only done in theory because in most cases they won't do that. So let's say we have a wire where current is traveling this way. We use the right-hand rule to show that the waves are actually heading out and rotating around the wire. And this happens in any wire that we're transmitting electricity through. So this happens in your keyboard wires, in your headset cables, in your phone charger. Any wire that has electricity, has charge moving through it, is going to create a radiation wave that rotates around. Now you can put shielding in the wire to kind of block that, which a lot of Ethernet cables have. But with the movement of electricity, you get this radiation. And we can measure that, and we get the wave that comes out and is transmitted away from your wire. And so that's how we do electromagnetic radiation. Now, there are a lot of different antennas, and the concept of an antenna is that you shape the wire so that it transmits in a specific direction. So here is our isotropic map, and this is looking from like the side, from a 3D perspective. Here's our isotropic, which means that it's transmitting equally in all directions. And a really common antenna is called the dipole, which just means that you have your signal coming in, and then it goes out to each wire. And you can see that here in the animation on the left. You can see the oscillation of the voltage and the current as it moves through the wire. And the nice thing about a dipole is that it actually creates this shape, this donut shape. And what that means is that with the wire pointing this way, right, the wire is perpendicular in the middle of the donut, then you are going to be getting the most signal strength in these directions around your antenna. If you are over here or down here, you're not going to get much signal strength at all. So this diagram here is a measure of how strong the signal is that you're transmitting in a certain direction. And in this case as well, the dipole antenna is perpendicular to these circles. Now, obviously, if you are above or below the antenna, that's not ideal. It's not a super ideal area to receive signals. Because if I'm trying to receive something from a satellite in space, and the satellite's coming down, I'm not going to be able to receive it well compared to if it was to my side. Because the antenna is designed to transmit and receive to the horizontally around it. So there are a lot of different antenna patterns, and if we're trying to transmit in just one direction, we're using a lot of our signal power to transmit in a bunch of directions. So to save power, we want to build our antenna so that most of the energy of the wave goes out in one direction instead of 360 degrees. And here it is. So what we do is we design, if we take a bunch of these dipoles and we put a reflector here, I think I can change the pen color. We put a reflector along the bottom here. What we see is we actually are able to decrease the original shape of the dipole and put more power in what we call the main lobe. So this is the direction that we want to transmit and receive. We're still transmitting a little bit in other directions, and that's just because we can't really get a perfect all-in-one transmission. But we're sending a lot more of our power in the direction we want to transmit. Now this adds the requirement to antennas that we have to point in the direction we want to transmit. And so satellites that are in space that want to transmit to Earth have to point at the planet. And if they're really far away, that can be difficult. Or let's say they get hit by a rock or something, and now their antenna is no longer pointing at Earth. So satellites will typically have two antennas, a low gain antenna, which means that it transmits in a bunch of different directions equally so that you don't have to point it, and a high gain antenna, which puts most of its power in one direction, again with some power coming out on the sides. And there are a couple ways that we measure the antenna gain. One is with the half power point, which is the width of this beam here. and another is with the distance from which we can receive and the amount of power transmitted. Now, antennas are kind of considered the black magic of engineering, specifically electrical engineering, just because there are 1,000,001 ways to shape your wire, and they're all going to give you slightly different transmission patterns. So we've come up with ones that work really well for us, but there are tons more, and there are even machine learning applications that will just iterate through millions of potential shapes of antennas to give us the best one for our application. It's still an open research area. There's a lot of work going into antennas. So now that we know how to transmit, let's talk about the frequency that we transmit at. So we know the electromagnetic spectrum. We've measured this over the centuries that we've researched it. And we know that different frequencies have different properties. The main property being what materials they can pass through. And you might have heard this if you learned about like gamma rays and stuff, the concept of needing to put a lot of water or concrete around a nuclear reactor because the waves can only transmit through so much of it. So we have a set of frequencies that we know work best in certain situations. At the bottom, at zero frequencies, we have our DC. And as we start oscillating our wave, we will see that we get things like 60 hertz to 100 hertz. And these are what we use for our power lines because they can go very long distances. The lower the frequency, the longer the distance, except for direct current. That one's a little weird. But in low frequency ranges, you can go very long distances because the wave, as it moves through space, one oscillation can be, several meters. It can be lots and lots of distance. And when a wave oscillates, it loses some percent of its power. And you can look at that with light as well. When light transmits, it loses its power and eventually decays. And with each step, this is one period, one oscillation of the wave. And so if the oscillation of the wave is spread out over tens of meters, you're going to get a much longer distance before your wave decays. But for the super high frequencies, right, where one of these waves is in the nanometers, you're not going to get much distance at all, unless you use a much higher starting voltage. But that requires a lot more power. And so that's why a lot of our communication stuff is in the kilohertz to gigahertz range. Because this we found is the optimal space to transmit data. Because we get enough distance and we also get a high enough frequency that we can actually put data on it. Because remember, we want the wave to oscillate multiple times for each symbol that we transmit. So if this is 101, the symbol that we're transmitting, we want the wave to have a high enough frequency that it oscillates many times in each of these symbols. And so the higher frequency the wave, the shorter the symbols can be, and the more symbols we can put in a second of transmission, therefore the more data we can send. So the higher the frequency, the more data we can transmit. But the trade-off is that the higher the frequency, the smaller the distance we can transmit over, or the more power it requires to go the same distance. And then there's another factor, which is that waves can only pass through certain materials at certain frequencies. And we'll talk about in a second. But what we find is that there are specific wavelengths They can pass through the atmosphere and actually reach space. You also have the visible spectrum, which we use quite frequently for lasers and optical waves to transmit data. It's a higher frequency, so we can put more data on it. And the visible spectrum, and specifically lasers, have very narrow beams. So when you transmit from an antenna, you are going to transmit out, and your power not only goes down over distance, but it also distributes over area. So if you're starting with, say, 100% power at one point, here that 100% has decayed a little bit by traveling this distance, and it's now spread out over this whole area. Lasers, on the other hand, have this unique ability to spread very little over very long distances, which means that your power is much stronger further out. But it also means that you have to point really well at the direction you want where your receiver is. Because if you can put your receiver anywhere in this area for the radio signal, but for lasers specifically, you have to put it exactly in the point that it's receiving. So it's benefits and drawbacks depending on your application. So here's what I'm talking about with absorption. We've measured over time that we can actually pass through the atmosphere at only specific frequencies. So here are radio waves in the megahertz. And so when you talk about satellites, they're usually in like the Ka band and the L band. And these are 1 to 2 gigahertz, or about 1,000 megahertz. And so this is the megahertz to gigahertz range. But this is really the only part that passes through the atmosphere, in addition to the visual spectrum, which is the light that we see from the sun passing through. So these are the only two frequency areas that we can actually talk to our satellites and have the satellites talk back. And it's been divided up very specifically so that satellites are using very specific ranges and they're not interfering and transmitting at the same frequency. But we can also use the areas where it doesn't get through the atmosphere to our advantage. And that's what we call a skywave. The idea of a skywave is that the transmitted signal is at a specific frequency that it actually gets reflected by the ionosphere and then, gets bounced back down. When they were first figuring out wireless communication and wireless transmissions, they believed that it had to be a straight line, that you had to be in line of sight to receive it. And there was an engineer, I think in England, who said, no, the wave is going to curve with the planet. It's going to curve with gravity. And so he set up a transmitter somewhere and set up a receiver somewhere else. And he transmitted, and he was able to receive the signal without line of sight. And he said, there you go, I've proved that the wave bends with gravity. And that wasn't exactly what happened. The wave actually bounced off of the atmosphere and went back down to the receiving signal. The waves won't bend with gravity because they have I don't believe they have mass. They're just energy. So what we see is that we can use we can use the reflection of the atmosphere to our advantage at specific frequencies. But this also has a negative side effect with higher frequencies in the gigahertz range, is that your Wi-Fi router is going to have trouble transmitting through concrete and metal and wood as the data rates go higher. And that's why we've seen a transition from one router in a house to a mesh network of routers that can give higher data rates, but you need one in every room because the frequency they're transmitting with can't pass through the walls in your house very well. So here are some common wireless communication systems. And what we're showing is the distance they can travel and the data rate. And so what we see here is that things that can travel not too far, so Bluetooth and Wi-Fi and such things, have a pretty high data rate in comparison to ones that can travel really far, like satellite links and satellite radios, that would be lower data rates. So what we see is that we want to choose a frequency to transmit at that gives us the desired range and the desired data rate. And for satellite links, this is a big problem because we need really high range, but that means we have a lower data rate. And we want to transmit, the 4K pictures from the Mars rover back to Earth. So we're going to use compression techniques. We're going to use data detection. We're going to put multiple bits into a symbol with those modulation schemes that we talked about. And we're going to try and pack as much data into the wave as possible because we can only transmit so much in order to be able to transmit at this distance. And so what that means is it's just a pick and choose scenario of what is our distance, how much can we transmit, how much do we need to transmit. And that determines how complex your system becomes. So as you can see, Wi-Fi has a much higher data rate than 3G, but it has much lower range. And 4G is up here with a much higher data rate and an equivalent range to 3G. And part of the reason we're doing that is because we have made more advanced compression techniques and we've made more advanced modulation schemes that allow us to pack more data into the wave. But we're also transmitting at a higher frequency. The 3G and 4G will transmit at a slightly higher frequency. And so while 3G is probably out here, 4G is going to be slightly less, and 5G will also be slightly less. But it's negligible compared to the amount of range that they can cover. And the reason that it stretches, right, is because if you have a 4G tower and you have a device that's here, it can use a higher frequency and transmit more data to you at a short range because it doesn't have to transmit as far. If you're over here, it might use a slightly lower frequency or method to go there. Or you could have two people near each other, but this guy has a lot of noise on his signal, so he has to transmit slower to avoid more errors than the guy who has a cleaner channel. So there are lots and lots of considerations that go into this kind of work. And as I said before, high frequency waves will decay faster and it needs more energy to go the same distance. Low frequency waves will decay slower, but you can't send data as fast because you need to oscillate a certain number of times in each symbol. A good example of this is if you're sitting in the back of an auditorium listening to a choir or an orchestra sing or play their instruments, then you're going to hear the lower notes better than you hear the higher notes because the higher notes will decay a little bit faster than the lower ones. It's also why people with lower voices are sometimes considered to talk louder if you're far away, because their voice is actually going to move farther through space. And also, as I mentioned, we're trying to send more data faster as we go and as we use more data. So we need to figure out how we can navigate around the physical limitations of a wave. How can we use the physics and try to like pack more data into a wave, try to transmit faster, and also how do we meet the timing requirements, right? Because if you're watching something live, if you're streaming Netflix, they are transmitting the data. They might be encrypting it, which takes time to encrypt and decrypt it. They have error detection and correction. They are encoding and decoding, and all this is happening in milliseconds of time between you interacting with the server and you watching it live. So where can you learn about this kind of stuff? The introductory parts are covered in 323 and 330. These are the ComTrack courses. If you want to get an idea for how waves and signals work, 323 is a good class to get that. I wouldn't recommend taking 330 unless you're really interested in the topic and the physics behind it. Unless you're ComTrack, then you have to. Compi 422 is DSPs, digital signal processing. That's going to give you the idea of how you actually process data in a signal. And it's going to go through a whole bunch of math. It's also somewhat introductory, but it's a pretty challenging course as well. Then you have the Compi 491 courses, which are cross-listed with the graduate level ENEE courses. These are where you learn about communications theory, about the modulation, about encoding and data rates. You'll learn about noisy signals and how to detect and prevent noise and how to handle it. And you'll also learn some transmission stuff as well. So they teach this stuff at UMBC. It requires a pretty heavy math background, but it is, if you found this interesting or you thought it was cool, I would definitely recommend it. Dr. LaBerge typically teaches these, and he is very good at this. He's been working on satellite systems and aircraft communication systems for his career. And that's it. Thank you guys for coming to this meeting. I'll stick around for a bit. People have questions or just want to talk or ask other things. If you don't, you are free to head out, and good luck with your 4 to 5 weeks left of school. Just to scare you all.